So I'm going to write an inequality on the board. A plus b over 2 is greater than or equal to the square root of ab. Now, I'm going to prove this inequality. So first, multiply both sides by 2. So a plus b is greater than or equal to 2 roots ab. Then we're going to square both sides to get a plus b squared is greater than or equal to 4 times ab. Then we can expand this square to get a squared plus 2ab plus b squared is greater than or equal to 4ab. Then we can move this to the other side to get a squared minus 2ab plus b squared is greater than or equal to 0. Then this factors into a minus b squared is greater than or equal to 0. And since every real square must be greater than or equal to 0, the statement has been proven. Now what I have just shown you is something that many mathematicians call the arithmetic mean geometric mean inequality, otherwise known as AMGM. However, AMGM can be generalized. So say we have a certain set of numbers, so a1 plus a2 plus all the way to an, all divided by the number of terms. This is known as the arithmetic mean, and this is probably the average that you have come to know, the sum of numbers over the count. But this is always greater than the geometric mean, which is a1 times a2 times a3 times a4 all the way to an. Then we take the roots, the nth roots. You can also write that this is all to the power of 1 over n, but normally this is how it would be written. Alright, now let's get into some applications of AMGM. Alright, and now your first problem is over here. So obviously we're going to solve this without using calculus, we're going to solve this using AMGM. So we're going to substitute x and 1 over x into AMGM. So we have x plus 1 over x all over 2 is greater than or equal to the square root of x times 1 over x. Now x times 1 over x is equal to 1. So we can write x plus 1 over x over 2 is greater than or equal to square root of 1. Now square root of 1 is equal to 1, so then we multiply both sides by 2 to get x plus 1 over x is greater than or equal to 2. And now we are actually done, because using AMGM we have proven that x plus 1 over x must be greater than or equal to 2. And because it must be greater than or equal to 2, we have solved for the minimum, which is equal to 2. And so we are done. Alright, that was pretty quick, so let's go on to the next problem. And now your second problem is on the board, or above the board, actually. So the important thing to notice here is that A, B, and C are interchangeable, meaning that you can change the order of A, B, and C, and the equation will still stay the same. So because A, B, and C are interchangeable, we can assume that A is greater than B is greater than C, and since they are all non-negative integers, it is greater than or equal to 0. Now with some observation, we notice that this equation's value decreases as C approaches 0. So to minimize the value of this equation, C must approach 0. Or in this case, we can set C to be equal to 0. So now we are left with A squared over B squared plus B squared over A squared is greater than 2. And now this looks an awful lot like AMGM. So what we can do is take this sum, divide it by 2, and then replace this 2 with a squared over b squared times b squared over a squared and take the square root. But a squared over b squared times b squared over a squared is equal to 1. So we get the square root of 1, we can move the 2 to this side, and now we know that a squared over b squared plus b squared over a squared is greater than or equal to 2. But the question does not ask for greater than or equal to, it asks for strictly greater than. So then the important thing here is equality. When does this equal to 2? And then we notice that we reach equality when each of these fractions is equal to 1. Or a squared over b squared is equal to b squared over a squared. Then we get a to the power of 4 is equal to b to the power of 4. And since a and b cannot be negative, this means that a is equal to b. But the question says that A, B, and C cannot be equal to each other. And so equality cannot be reached, and this is strictly greater than 2. And so we have proven the statement, and we are done. Now, on to the final. problem. Alright, and now our last problem is above me. Unlike our other problems, the application of AMGM isn't quite clear here, but we do notice that we see x times the sine of x pretty frequently. So we can substitute y is equal to x the sine of x. So then we get 9y squared plus 4 over y. But then we notice that this is equal to 9y squared over y plus 4 over y, which is equal to 9y plus 4 over y. And since 0 is lesser than x is lesser than pi, y cannot be equal to 0, and so this is okay. Now, the application for AMGM seems pretty clear here. We have 9y plus 4 over y over 2 is greater than or equal to the square root of 9y times 4 over y. So then we get 9y plus 4 over y is greater than or equal to 9y times 4 is equal to 36, and we can cancel out the y's to get 36. The square root of 36 is equal to 6, and then 6 multiplied by 2 is equal to 12. So we get 9y plus 4 over y is greater than or equal to 12. We can substitute x sine of x back in to get the expression that we had at the top. And so now we know that the minimum value is 12, and we are done. Alright, thanks for watching. I know this video was probably kind of short, so in future videos I'll probably come back to this topic and looking at much harder problems. So yeah, thanks for watching. Hopefully you enjoyed, and hopefully I'll see you next time.